In this video, we're looking at the cyclotron motion of a solar wind electron that enters the Earth's magnetic field at right angles. So we're given a speed on this electron of 6 times 10 to the 5th meters per second, and we're given the strength of the Earth's magnetic field at this point as 0.1 Gauss. Now the conversion to Tesla is by a factor of 10 to the 4th. Gauss are the smaller units. So this is 0.00001 Teslas. And in part A, we're just looking for the qualitative direction of the magnetic force on this electron. So when I look in the diagram, our point of view is such that the magnetic field points directly into the page. The velocity of the electron is 90 degrees to that because it's in the plane of the page. And we're trying to figure out the direction of the force here. So to get this done, we have to use the Lorentz force right-hand rule, and I'll post a link real quick to where this was first introduced. There are actually 3 different ways of using this right-hand rule that I'm aware of. My favorite method is to put my fingers of my right hand in the direction of the velocity and then sweep out to the direction of the magnetic field, which is into the page in this example. So it looks like this. Now notice that my thumb is pointing this way. That's the direction the force would be on a positive charge. So in the Lorentz force right-hand rule, it gives you the direction of force on a positive charge. If the charge is negative, you have to reverse that direction. Now there are other ways of using the Lorentz force right-hand rule, and you can just pick whatever one is your favorite. Another one that you might use here is to put your fingers in the direction of the magnetic field. So you pretend your fingers on your right hand are the field lines. Put your thumb in the direction of the velocity vector. The force would point out of your palm, which again is down and to the left. And then you have to say, wait a second, this charge is negative and I need to reverse the direction of that. And we arrive at the same direction for the force vector. So there it is qualitatively. And what this force is going to do is it's going to cause the velocity vector to rotate in the clockwise direction. That velocity will stay in the plane of the page, so the electron is always moving perpendicular to the magnetic field. The speed never changes, and the velocity vector simply rotates, and the path of this thing is curved into a circle. So there is some radius of curvature to this motion. And that's what we're looking for in part B. So to get at the radius of curvature, we have to do a force analysis. And I'm just starting by stating Newton's second law, F net equals ma on this electron. And what's the net force it feels? All it feels is the Lorentz force here. And its acceleration, that's related to the speed and the radius of curvature. That's v squared over r. Now the magnitude of the magnetic force on this electron is given by QVB times the sine of theta, where theta is the angle between the velocity vector and the magnetic field lines. Well, that's 90 degrees, and the sine of 90 is just 1. All right, so we're left with QVB equals mv squared over r. We can cancel one factor of v. And what we're trying to solve for in this problem is the radius of curvature. So I multiply both sides by r, and then divide by QB. And I find that the radius of curvature is mv over QB. Now all we have to do is plug in our mass for the electron. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. The speed of the electron, we were told, is 6 times 10 to the 5th meters per second. The charge on the electron, I'm just working in magnitude here, is 1.6 times 10 to the negative 19 coulombs. And the strength of the magnetic field was 0.00001 Tesla. And when I plug in the numbers, I get 0.342 meters, just keeping 3 sig figs, which might be nicer to state as 34.2 centimeters. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.